Hi, my name is Hussain Liaquat, and I'm a staff software engineer in test with the Test and Tools Infrastructure Department. Today, I'm going to talk about how we are helping teams in GitLab select the best AI model and provider when it comes to latency. But first, I would like to call out the team behind this work and thank them for their contributions, starting with Abhi, Mark, Yevgen, and of course myself. I would also like to thank Mark for reviewing this deck in detail and also for helping out with the suggestions. Our users expect near instantaneous responses. Low latency minimizes the delay, making interactions feel more natural and fluid. This becomes even more important when the user is a developer. When developers are writing code, they need suggestions or completions to appear almost instantly to avoid any disruptions. High latency can break the developer's flow and cause frustrations as they have to wait for the AI to catch up with the typing. Continuously evaluating latency helps us in early identification of models with optimal performance and provide competitive advantage in delivering AI-powered services. For GitLab, the ability to offer consistently low latency AI services differentiates who need to optimize developer efficiency. For users, this results in a better development experience, faster feedback loop, and overall enhanced productivity. To determine the model for code completion that provides the lowest latency, it is important factorization as well as the location from where the model is served. The problem with the existing approach for evaluating AI provider latency as experienced by the GitLab users was that it required a full GitLab end-to-end setup, which is time-consuming and resource-intensive. We wanted to have a more efficient solution to provide to quickly test multiple providers continuously in different geographical locations. As a result, we introduced the AI model latency tester. Now, with the AI model latency tester, we ensure that the prompts sent to the provider have the same format and context that GitLab constructs from users' input. We directly call the AI provider's API. It is bare metal. We provide a dashboard to compare the latencies and help in making decisions. We created a solution around an existing tool, the prompt library, which was created by the AI model validation team. We did not go with creating a tool ground up. Now let's go through some key definitions. Code suggestions is the name of the GitLab feature we are evaluating, which is in full called GitLab Duo Code Suggestions. It's also used to refer to the feature more broadly, that is, the capability of the product itself. For example, users can install GitLab Duo in their IDE to get code suggestions. Code completion is the code that appears as suggestions on the line or the line below as you are typing, and after you stop briefly. It is usually relatively short suggestion of a single line or sometimes 2 to 3 lines. Code completion usually does not need any textual instructions sent to the model. Code generation is the code that appears as suggestions after you press enter following a code comment. It is usually at least a few lines of code, but potentially many more depending on the complexity of the code of the comment. For code generation, GitLab sends some contextual instructions to the AI model. For code completion, it does not. With AI model latency tester, we are currently only focusing on code completion feature, but we are not only evaluating models designed just for code completion. We are also evaluating models designed for broader use, including code completion, code generation, and code generation. In future, we are planning to expand the evaluation to code generation and other GitLab Duo features as well. Now let's talk about the types of AI models we are evaluating. The first one is chat-based model. Chat-based models are models that accept plain text as language, accept plain language text as input, and respond in plain language, possibly including code. For example, Anthropic's Claude Sonnet models are chat-based models. The majority of the models we are evaluating fall into this category. Code-based models are models that accept code as input and respond with code. For example, Google's CodeGecko is a code-based model. Both types of models can be used for either code completion or code generation. The important difference for our use case is whether instructions are needed. If a model isn't designed to accept and return code, GitLab needs extra input handling to translate the user's context into suitable input for the model. It also needs extra response handling to extract just the code from the response that includes plain language comments. As I mentioned earlier, the AI model latency tester uses the prompt library. This is the architecture diagram in front of you. Prompt library takes configuration files and prompts as input. The configuration files is where you specify things such as the model to test, its parameters, which languages to use for the prompts, the batch size for the calls made to the AI provider, the input and output BigQuery tables where the data is stored. Since we are evaluating multiple models, 16 to be exact at this stage, and the list is growing, managing the configuration files became difficult, so we created just one YAML file per run type. It has all the models and their settings unique to them. And then we generated the config files at runtime from that one YAML file. We have runners deployed in GCP in 3 regions that match the AI gateway deployment regions. We run evaluations from those regions, taking prompts from the input BigQuery table and writing the results to another BigQuery table. We hit the servers that are closest to those regions in most cases where the clients are. In some cases, the servers are only in the US, such as in the case of Claude 3.5 Sonnet hosted by Anthropic. In case of Cloudflare, Phi2 and OpenAI, the traffic is dynamically routed to different servers via their load balancers. Once we have the results in the intermediate table for each client region, we collate it and save it to a single results table, from where the Looker Studio dashboard reads and displays the results. Now let's talk about the individual components, the architectural components briefly. Prompt library, as I said, allows users to conduct testing on various prompting techniques across different LLM vendors, supporting decision-making process backed by data. It's a Python library with CLI interface that exposes the different use cases and pipelines. It was created by the AI model validation team. BigQuery stores data using a column storage format and is optimized for analytical queries. BigQuery presents data in tables, rows, and columns and provides full support for database transaction semantics. Looker Studio, formerly known as Google Data Studio, is a cloud-based business intelligence tool that allows users to visualize and share data in the form of customizable dashboards and reports. It integrates with various data sources like Google Analytics, Google Ads, BigQuery, such as in our case, enabling users to turn raw data into insightful reports. And then the AI model latency tester. It automates the evaluation of latencies of third-party AI service providers, using clients in different geographical regions to simulate experience of geographically dispersed users. It aims to assist in making data-driven decisions regarding which model should power GitLab AI features. Use the prompt library Docker container running in CI in CI runners that are VMs on GCP. Runners are deployed in multiple client regions that may match the AI gateway deployment regions. Those regions are in US, it's US East 4, Europe West 2, and Asia Northeast 3. These represent the client regions. Although there are more regions the AI gateway is deployed on, currently we are only matched these 3 regions, and we have plans in future to expand. For some providers such as AWS Bedrock and La Plateforme, we run evaluations from the client regions in series to stay within the rate limits. For other providers, we run the evaluations in parallel in all 3 client regions. Here's a list of the models we currently evaluate grouped by the providers. These are 16 in total currently, and they may grow in future. Some models are evaluated on the servers of their creators and also on popular cloud providers. For example, Cloud 3.5 Sonnet by Anthropic is deployed on Anthropic's own servers, as well as on Google's Vertex AI and Amazon's Bedrock. The Codestrel Chat and Codestrel FIM are basically the same models, using different interfaces and messaging formats. FIM is a short form for fill in the middle. It accepts prompt as code. It also optionally accepts suffix. So if both prefix and suffix are provided, it fills the code in the middle, and hence the name fill in the middle. For most of the models and providers, we run evaluations against their servers hosted near to the client regions. If a server is not available in that region, we evaluate against the server in US. Some providers route the client requests through a load balancing system, such as in the case of Cloudflare. Anthropic servers are in the US, but their location has not been disclosed to us. Similarly, OpenAI servers are also in US, but they have not documented their exact location. The parameters for the model are set to default value in the prompt library code, and we can override them in the YAML configuration. In our evaluations, we match the value of the parameters to GitLab's value, the values that GitLab has in its code. Some notable parameters are max output tokens or max tokens is the maximum of new tokens that should be generated in any request to the model. For code-based models, such as CodeGecko, this value is set to 64, and for chat-based model, it is set to 512. There's an upper limit on code-based models. Input token limit is the upper limit of the number of tokens in the input prompt. For code-based models, this value is set to 2048, and for chat-based, it is set to the max value that's supported by the model. We also use stop sequences, which are used to make the model stop generating tokens at a desired point, such as end of a sentence or a list. For code-based models, this value is set to double \n. And for chat-based models, where we send contextual instructions, this value is set to closing new code tag. We specifically instruct the model to insert its suggestions between the opening and closing new code tags. Temperature is a parameter that controls the randomness of output generated by the AI model. A low temperature results in more predictable and conservative output. For most models, the temperature is set to 0.2. Let's talk about the input prompt data. The prompt data used as input for the models have these characteristics. Total 140 prompts per model per region. We keep the prompts limited to this number to avoid any rate limits and keep the costs controlled. It has a mix of JavaScript, Go, and Python scripts. The prompts sent to the model by the prompt library is a partial or incomplete code taken from files from multiple public GitLab-owned repositories. The input length of the prompt varies between 100 characters to 13,000 characters. For chat-based models, the prompt is accompanied by some textual instructions. Once the call is made to the model's API, we wait for the full response last byte and capture some data. Some of the data are response time in milliseconds. This is the round trip time to last byte. Model completion is the response body from the model. Expected completion is the ground truth, corresponding to the actual code following the snippet from which the prompt was constructed. Lang ID is the language of the input. Prompt final is the final prompt that was sent to the model, including any contextual instructions. Once the evaluation data is available in BigQuery tables, it is visualized with Looker Studio. Here are a few snapshots taken from the Looker Studio, and next we'll do a quick demo of the dashboard in Looker Studio. We have quite a lot of tables, and I'm not going to talk about all of them, but I'll go over a few. The first table is the summary page. On the summary page is the dataset details and the model configuration. Description of some of the fields are mentioned at the bottom over here, but I'll talk about a couple. The maxed output token is what we specify on the model. It is the maximum number of tokens the model will output in its response. The average input token is calculated from the model's response. It is an estimate. Every model has its own way to calculate the token. On an average, 4 English characters correspond to 1 token. The second group of tables lists comparative latencies for models with the servers in specific regions that match the client's location. As we discussed earlier, some models do not have the servers in the same region as the client. The server region column is clear in calling those out. For example, La Plattforme, Coastal FIM has just a model in Sweden, but OpenAI GPT-4o Mini, it does not specify the server region, and the servers are distributed dynamically. I'm not going to talk about the temporal latency trends, as it's pretty obvious and self-explanatory. Next, we have tables for latency response to increasing prompt sizes and suggestion sizes. We can notice that the increasing prompt size, that is the input to the model, does not always have an impact on the latency as it increases. However, the increasing suggestion size, that's the output from the model, does increase the latency as the size of the suggestion increases. Now, this will be more obvious when we see the graphs for individual models later on. So if you see that if the size of the input is between 0 to 100, the latency is around 1000, but as we increase the size of the input, the latency size increases as well. But that's not the case for increasing prompt sizes. So in case of La Plattforme, 0 to 1000 prompt size has approximately 1100 millisecond latency, but when it increases to 2000 to 3000, it's under 1000 milliseconds. But this will be more clear when we move on to detailed tables. We also have separate dashboards for each model type. Let's go over to Claude Sonnet 3.5. The Claude Sonnet 3.5 model is served by Anthropic. AWS Bedrock, as well as Vertex AI. Let's look at the graphs for AWS Bedrock. The AWS servers closest to our clients are in Asia Pacific Northeast, Europe Central 1, and US East 2. We have clearly mentioned on the top. The client and the servers are clearly mentioned. The first graph, this one, shows the P0, P50, and P90 latencies for each client and server location. The second table shows P50 latency numbers for the client and server locations on a heat map. So it looks like Europe to Europe provides the least latency among all three. Asia to Asia and US to US are approximately same. This third graph shows average response time for different prompts, that's input sizes. We also discussed this earlier, that the size of the prompt does not have an impact on latency unless the input is very high. The third graph, the fourth graph, shows the response time based on the model's output size. It shows that the size of the output does have an impact on latency. So as the size increases, the latency increases. The last graph shows the model's performance breakdown per language. We are only evaluating Go, JavaScript, and Python. It looks like prompts for Go language have the highest latency and Python has the lowest. This is just for Claude Sonnet 3.5. So what's next? We have an exciting lineup of upcoming features and enhancements. This slide lists some notable ones. We are planning to increase the scope of latency evaluations to other GitLab Duo features, with code generation and Duo chat as the next highest priority. We will be deploying AI Gateway to multiple regions and will perform the evaluations via the AI Gateway. We plan on running the evaluations multiple times a day for better representing user demand throughout the day. Currently, we send the prompts as user prompts only. We plan to break it up into system and assistant prompts. Contextual instructions such as "you are a tremendously accurate, skilled coding autocomplete agent," for example, this will go into the system prompts. We are currently using CI runners as clients that are deployed to 3 regions in VMs on GCP. Deploying them takes time, and since we have to keep them up, it is costly. We are planning on shifting to GCP Cloud Runners to spin up the VMs on demand. So that's it for the slides. I'm happy to take any questions.
Probably it will be helpful if you can talk about how we like the use case with AWS Bedrock for Claude 3.5 and how we have evaluated the latency patterns for that and with the external stakeholders.
So we did some comparison. I'm going to give you a bit context on what Abhi is probably talking about. We did a comparison between the three different providers for Cloud Sonnet. The first one is the Anthropic servers themselves. Then we have on Vertex AI, and we also have it on AWS Bedrock. So we did some comparative studies and we found out that AWS Bedrock's response times are the slowest. So we we set up a meeting with the AWS Bedrock team, and we showed them our results, and we showed them the comparison with Vertex AI, which was the fastest. So and we had a chat with them. They agreed on taking this to their engineering team, and they will look into why the latencies are slower for them. They were thinking that they had the fastest latencies, but our data was clear, and we are performing the same kind of evaluation on all three servers, on all three providers. So why is there the slowest? So we are still in process, and they have taken this up with their engineering team, and once we have some feedback from them, uh, we'll know how to proceed.
Yeah, to add to that, I mean, there has been a question when we started this initiative is like, hey, why we are like from GitLab, why we are doing it? Why like the third party systems, like they have their own testing and data regarding their models, why can't we leverage that? So this is an epic case of it. Like when they have shown their results, it was like quite a few second order of faster against like our results. So it's also based on the prompts that and the contextual instruction that GitLab is like sending to the models, and we have seen the latency differences through those contextual like instructions and the differentiations of the prompts that we are using as a test data. So that also got recognized.
If there aren't any further questions, I'm happy to wrap up.
Sorry, I had one.
Yep.
Getting distracted. You said was it OpenAI? They're not happy to reveal the locations of the servers
For
in America. Is that right?
that was for Anthropic. Anthropic's,
Anthropic.
yeah, Anthropic. They did not reveal their locations to us.
How can we? How do we verify the results then with that? Because it could change each run. It could be hitting a different server if they have multiple servers, for example.
Yeah, we are not verifying where the requests are going. We just mentioned that clearly in the dashboards so that the whoever is looking at the dashboard, they are aware that this can be any region. So unfortunately, we don't have a way to find out where the request is going and where it is ending up.
Do we know if the test results are quite spiky because of that? Are they quite varied, or are they still quite consistent? I'm just curious.
I think they are consistent. We can take a quick look again. So we're talking about Claude Sonnet on Anthropic. We had one spike on 8th, on the 7th, but after that it has been quite consistent. Not a lot of change.
That's fair. No, I was just curious. That's fascinating to see how all these different providers operate. It's certainly quite the challenge.
Yep. Are there any further questions? All right then. Thanks for joining. See you later.
Good
Bye.
decision. So bye, take care.